So tonight, last week, we graduated from confidence intervals for means and for proportions. And we went from them and we just started to taste the idea of comparing means of two populations. We started with single sample t-test. We just got the very first introduction to that. So let's see where we've been. We've been through confidence intervals where we knew the population standard deviation, right? So we could calculate the confidence interval with a lot of confidence. We could use sigma, since we know what sigma was for the population. We could use the standard error for the distribution of sample means for any particular sample size equals sigma over the square root of n. I'm going to do that on paper in a moment. And we understood that we really understood a lot about the way samples are distributed if we know what the population looks like, particularly the standard deviation or sigma for the population. Unfortunately, we very rarely know that. Most of the time, we're guessing at the population mean and at the population standard deviation by using our sample. So we have a sample of size 100. We have a pretty nice idea what the mean is, and we have a pretty nice idea of what the standard deviation of the population is, because the sample mean, when we have a very large sample, approximates the population mean. And the standard deviation of the sample, when we have a very large sample size, approximates the standard deviation of the population, sigma in other words. Well, the problem is that a lot of times we don't have a large sample. A lot of times our sample is relatively small, 25, 10, and so on and so forth, right? To a matter of resources, right? So in those cases, we have to make up for the uncertainty that we've introduced by not really having a good handle on what the population variability is, what the standard deviation is. So instead of using the Z table when we calculated confidence intervals, we had to use something else called a T-distribution or T-table, right? And the T-distribution makes up for that extra variability. And in fact, there's a T-distribution for every sample size. As we get to a larger and larger and larger sample size, the T-distribution for that sample size looks more and more like the normal distribution, like the Z distribution or the Z table. Fortunately, we don't need 8 million tables, because all we're really interested in is what the value of T, we're using in the place of Z because we don't know the population standard deviation, what the value of T has to be for any particular sample size for 95% certainty, for 99% certainty, or say for 90% certainty, but certainly for 95. So we don't need really all those other numbers in most cases. We just need to know for our particular sample size, what should we use instead of 1.96 for a 95% confidence and calculating 95% confidence interval, right? So we went from there, understanding that, to applying it to a situation where we knew what the population mean was for one population, but we only had a sample from a second population. And we said, okay, so now can we tell with a relatively high level of certainty, like 95% certainty, less than 5% chance of being wrong, what we call our alpha errors, less than 5%. Can we tell to that level of certainty that the means of these two populations are different from one another, right? So we decided, well, we could kind of extend what we know about the confidence interval and look at it from another angle and turn that into something called a t-test, where we look at the difference between the mean for our sample and the mean for this population. Are they different enough? Are they far enough apart? How many standard deviations, how many standard errors, because we're dealing with a sample, how many standard errors apart are they? And are they enough standard errors apart for us to say that there's less than 5% chance that we would get them that far apart if the two means of the populations weren't different? In other words, if our null hypothesis was not true, right? Or was true. So we want to show that the likelihood that our null hypothesis is true is so low that we'd only get them that far apart if less than 5% of the time if the null hypothesis was true. So I'm going to go back and just do a couple of quick examples of confidence intervals with standard deviation, knowing the standard deviation, not knowing the standard deviation, and using the t-test. I'll do a couple of them. One, standard deviation known, standard deviation unknown, and then I'll also do one other one for proportions, since that's also a point value, and we might actually be using the t-test for proportions as well. Okay, so let me get those out. And what I've done is I have a special version of this, and I have to get back here to get to it. If I can find it, let me see where it is here. Oh, there they are. Okay. All right, I've got them in an Excel file. Actually, I could use a PowerPoint. PowerPoint's easier, probably. Let me not open up PowerPoint. Okay, it's a special Halloween version. We'll get to that. What I do here, okay. Let me get the PDF version of this. There we go. All right. So, being Halloween, there's a lot of monsters walking around. I have, but when you go home, they'll be throwing eggs at your door and stuff like that, and they'll be banging on your door for candy and stuff like that. Some of those will be actual zombies. I can tell you that right now. They're hard to tell apart from the actual children, but some of them may actually be zombies. So here's the deal on this, okay? So as it happens, we know this is a zombie food pyramid. Like you guys, do we have any nutrition students in this class? Probably not. Probably all public health people, right? Or EOHS. There's all EOHS people in this. No, maybe not. Let me think about that. BIOS, probably a combination of EPI and EOHS and so on and so forth. No nutrition. And Hunter, I got a lot of nutrition students. So, we're all familiar with the food pyramid and stuff like that, right? Like carbohydrates and down here's vegetables and stuff like that. Zombies, this is their food pyramid. Their main food group is brains, and then liver, heart, like internal organs, stomach and so on. And then the gristle and bones and stuff like that. They just eat a little of that, right? So, but they like brains. So, because they eat so much of this kind of stuff, we're a little concerned about their cholesterol levels, right? So let's calculate the 95% cholesterol level for the mean, 95% confidence interval for the mean cholesterol level for all zombies, for the entire population of zombies. So the zombies' primary food source, high in protein, carbohydrates, serum cholesterol levels. We captured 25 adult zombies, and we measured their cholesterol levels, and we found that the sample mean was 151.4, and I guess, what is that, milligrams per deciliter or something like that? There's some measurement like that. 151.4 is the mean of our sample. The population standard deviation, sigma, that for the CDC's done a lot of studies on zombies. You don't know about it because like Area 51 is like they don't tell you about this. They don't want you to know about the virus, right? They don't want to cause panic. You don't know about it. They've done a lot of studies on it. So as it happens, we know what the sigma is for all zombies, right? We know that the standard deviation sigma for all zombies is 38 milligrams per deciliter. Okay, the mean is 151.4. So okay, so let's see what we know here. What we don't know, what we know, what we don't know. Okay, so for starters, 151.4. What, 151.4? What is that? Is that mu or X bar? X bar, right? Okay, that's right, because it's a statistic, right? That's a statistic. Okay, and what about 38? That's sigma. That's a parameter. That's, as it happens. Normally we don't know this kind of stuff, but as it happens, we do know it for in this particular case, and it happens to be the. I want to make sure I'm muted here for everybody. Okay, good. Okay, let me get my pen back. Okay, that's a parameter. It's the population standard deviation, which gives us the latitude to use the z-scores instead of the t-distribution. Okay, so in order to create a confidence interval now, what is our confidence interval going to be? It's going to be X bar plus or minus some value. In this case, we're going to use z. The value of z that's appropriate for an alpha error, chance of being wrong of 5%. A lot of times you'll see that instead of seeing alpha is equal to 0.05 on the bottom of that z, you'll see alpha over 2 equals 0.025. It's the same thing. What they're saying there is that each tail is 2.5%, lower tail and upper tail, right? So either one of these is, and then you might see a comma, and then you might see DF the degrees of freedom are n equals 20. Actually, with this, you probably won't even see that because we don't need to worry about degrees of freedom here, right, for the z-score, right? So times the standard error, right? Some z-value times the standard error. So what is that z-value? If we know standard deviation of the population, that z-value is going to be 1.96 for a 95% confidence interval, 2.58 for a 99% confidence interval, and 1.64 for a 90% confidence interval. That comes from the z-table, right? So this is for a 95% confidence interval, 99% confidence interval, and a 90% confidence interval. Notice that making that z 2.58 means that this number, when we multiply times the standard error, is going to be bigger than for a 95% confidence interval. So when we subtract and add a bigger number from x bar, it makes it a wider confidence interval, which makes sense. It has to be wider for us to be more confident, be 99% confident instead of being 95% confident. Okay, so let's analyze and see what we got. So 151.4 plus or minus 95% confidence interval is going to be 1.96 times our standard error. What's our standard error going to be equal to? The standard error is equal to sigma over the square root of the sample size, which is 38 divided by the square root of 25 is 5. So that's going to be 7.6. Okay, so standard error is going to be 7.6. Okay, so our 95% confidence interval is going to be equal to, and I get my calculator out. Oops. Okay, I'll put it over here. Okay, so it's going to be 1.96 times 7.6. And I'm going to clear memory just to make sure nothing's in there, and I'm going to add it to memory and clear this out. So that now is my margin. That 14 was my margin of error. This is called my margin of error. Okay, so I'm going to take my 151.4 and I'm going to subtract my margin of error, recall it and subtract it, and I get 136.5. And our upper limit for our confidence interval is going to be, okay, I'm going to clear that out, 151.4 plus our margin of error is equal to 166.3. So that's my 95% confidence interval. Okay, now if I repeated this for 99%, what would I do? I would just change this number, plus or minus 2.58 times 7.6. 2.58 times 7.6. Okay, and calculate that. Or do I need to calculate that? Or you guys are okay with that, right? Yeah, okay, and for 90%, 151.4 plus or minus 1.64 times 7.6. Should I go over like where that came from, where those two numbers came from? 2.58. What's from the, not so much the empirical rule, but from the table, the Z table. Let me show you that. Since I was wondering about that, let me just show you where these numbers came from. Okay, so now we're looking at in terms of these confidence intervals, we're looking at the areas. Now for 95% confidence interval, we're looking at the samples that would fall within 95% of the population mean. In other words, 136.5 to 166.3, 95% of the, we're 95% certain that the true population mean is between these two numbers. If I repeat this 20 times, my confidence interval, if I take another sample of 25 people, 95% confidence interval means that if I do it 20 times, get a different mean each time and a different confidence interval, 19 out of 20 times, the true mean will be between those two numbers. Not 100%. If I wanted to be more certain, I would go 95% confidence interval, make it wider. So then 99 times out of 100, I would expect that it would be likely that I would capture between those two numbers I calculate the true population mean. Okay, and the place where these come from is this idea of, well, 95% of these samples are within this range of the true mean. Okay, so this is 2.5% on this end and 2.5% on this end. As it happens, from the empirical rule, we knew this was z-score of 2 and -2, -2 and +2 standard deviations. But actually, in real life, the empirical was just an estimate. It's really 1.96. To get a 2.5% at this end and 2.5% at this end, the z-score is really more accurately -1.96 and +1.96. Similarly, to be 99% certain, right, it has to be 2.58. And to be 90% certain, in other words, 5% at this end and 5% at this end, it can be as low as 1.64. And I'll show you the Z table to confirm that. Okay, here's the Z table. So let's take a look at what the Z score has to be for this area here to be 2.5%. In other words, 2.5% on the low end, 2.5% on the high end. So what does the Z score have to be for 2.5%? So here we go. Here's 2.8%, 2.81. Okay, and here it is right here, exactly 2.5%. What Z score is that? It's -1.96. And what about for 99%? 99%, this area would have to be 0.5%, 0.005, right? And then you have tail at the other end, the other 0.005. So the area between them is 99%, right? So we're looking for where is it? 0.005, 0.001, 0.0, okay. Here we go, -2.5. So here we are right in here, one of these two, right? 2.5 looks like either 7 or 8. I'm going to choose 8. Okay, -2.58. So our 99% confidence interval, 2.58. And for a 90% confidence interval, where only has to be 5%, is 1.64. This is 1.6. Where is it? 1.6. And it could go either way here. I chose 1.64. Right? That's where we got it. That's the areas, the actual areas of the curve from the Z table. That's what. So those numbers, I didn't invent those numbers, you guys. Okay, so now you guys know that there's a real reason for those numbers. It's not something that I just completely made up. So yeah, and again, all you'd have to do to calculate 99 and 90% confidence interval is substitute for the Z score, 2.58 and 1.64. Okay, so yes.
So we know that the tails are 2 standard deviations away from the mean.
Yeah, really 1.96.
Oh, so
right.
You can't do the opposite. You can't look at for the Z score for 2.
For 2, yes, because we use the empirical formula, but 2 is only an estimate.
So that's
right. It's really 1.9. When we gave you the empirical formula, we were lying, right? We weren't lying. That the empirical formula is an estimate, right? Empirical rule is an estimate, right? It's not, and like we said, that 3 standard deviations was 99.7. Well, it's really maybe 99.6 something or so. And 90, I think we said for 95%, 1 standard deviation, I think we said it was 68%, and it's really like 68 point something percent, something like that. But it's an estimate, not the empirical rule is just a quick estimate. Okay, and it's useful because you can use it to wrap your head around. You know, like when you say 95%, you say to yourself, if you look it up on the table and it comes out 1.75, so well, wait a second, that's not right. It should be close to 2, right? So you know 1.96 makes more sense. Okay. So repeat the study above without assuming the population standard deviation for zombie cholesterol is known. Okay, we're assuming that it's not known. Okay, so this time our sample standard deviation, again, took a sample of 25 zombies. The sample mean was 151.4. Now we don't know sigma, so the only source that we have for the standard deviation of the population or estimate of it is the sample standard deviation. I may believe that we got it right on the nose. By accident, we got exactly 38. But we don't know that. So we have to assume that we don't know it all that accurately because we're estimating it from that small sample that we took. So not only is the sample mean an estimate, but now the sample of the population, but now the sample standard deviation is an estimate of the population standard deviation. So we don't know it very well. So we know now we need a wider range for our confidence interval to make up for that extra level of uncertainty. So how do we do this? Okay, so we're going to calculate the standard error and the confidence interval, 95% confidence interval for this situation, which is really the same numbers as before. So how do we calculate that? It's going to be the same formula. I'm sorry? Yeah, T. X bar plus or minus, you're exactly right, except this time instead of Z, I'm going to put T here. And then I'm going to multiply it by the standard error, okay, which we're going to calculate the same way. Okay, now on the bottom of this T, I am going to put alpha over 2 equals 0.025. I could also just put alpha is equal to 0.005, right? In other words, I'm saying I want 95% confidence, the T score for 95% confidence. I'm going to hit comma, and I put degrees of freedom equals 24. In other words, I'm putting not only the T, not only do I have to consider what level of confidence, the alpha error that we're willing to accept, but also what sample size I'm working with. I put 24 instead of 25 because the degrees of freedom are equal to the sample size minus 1. Okay, so let's see what this is going to be. So now it's going to be 151.4 time plus or minus the T that we need times our standard error. Now, what's our standard error equal to? Standard error normally is standard deviation over the square root of the sample size, but we don't know the standard deviation of population. So we have to use the standard deviation of the sample over the sample size. Happens to be 38 over 5 again, 7.6, but we don't know that we got it exactly right. Just came out that way by chance. So we still have to use T, right? Times 7.6. Now, what do we use for T? We have to go to a table to look up what T has to be, okay? And T is going to depend on the sample size, degrees of freedom, and on how accurate we want to, what kind of risk we want to take with our confidence interval. So I'm going to go in here and I'm going to say, I use the Agresti table. You can use the one in the book. It doesn't really matter. They're all the same table in the end. Oops. Why is it making? It's escaping every time I try to move over to it. Okay, let me see if I can just, I don't want this Z table. Agresti. Okay, Agresti T table. Can I space down? Yeah, I can space down. Good. Okay, good. I don't have to move my thing. Okay, so in our case, we now have to scroll the pointer. We now have to scroll down to, first of all, confidence level. What confidence level do we want? 195%. Right tail probably, see, there's our T 0.025, because you're just looking at one tail is 2.5%, but then you got to consider the other tail too, another 2.5%. So that means 95%. Okay, so I'm going to scroll down until I get to 24 degrees of freedom. 24 degrees of freedom is a T score of 2.064. What are we doing here? We're adjusting for the use of the standard deviation of the sample instead of sigma for the population. So what does this do? This is a bigger number than 1.96. So when we multiply it times 7.6, the standard error, we're going to be adding and subtracting a bigger number from X bar, which makes the confidence interval a little wider, making up for our extra level of uncertainty, right? So, and you'll notice that as the sample size gets smaller, what happens to what the T value we have to use? It gets bigger and bigger and bigger. And as the sample size gets bigger, what happens? It gets closer and closer and closer. Ultimately, if you're doing the whole population, it's 1.96 because you know the whole population. So the standard deviation, if your sample is the same as the size of the population, you know your population sigma, right? So that's,
on that table,
yes.
does it mean that the scores between 60 and 80 follow the?
These other columns, you mean?
No, on the degrees of freedom.
Oh, down here? Yes.
Yeah, like the scores in between.
Oh, you know, you got two choices there. In other words, if it's 84, right? If your sample, if your degrees of freedom is 84, well, you could just say, I'm going to be conservative. I'm going to go to 1.99. You take the worst word. In other words, your choice, if you're in the middle, you would either go 1.99 or 1.984, right? But the more conservative choice is to go here to the smaller sample size, right? So yeah, you could try to interpolate. In other words, there's 20 difference between these, and take the difference and divide it by 20. What's that?
Why not, why table, why that? Why not give us all the numbers?
Because I only have one page to do it. Right? They could have given you a Z table for every sample size, right? 2 pages for every sample size. And then, like you said, you could, if you wanted to, do a 64.5% confidence interval, right? Because you'd have the whole table, right? But that, it's an abbreviation. Like I said, it's you don't have to worry about it being this precise, because eventually in real life, what are we going to use? We're going to use SPSS, or we're going to use Excel to do this. And SPSS always uses the exact t-value. It doesn't matter. A lot of textbooks, a lot of instructors will tell you, if the sample size is large, that you can just use 1.96, right? Because you're getting so close anyway. What's a large sample size? Some books will say 100. Some books will say 50. Some books will even say 30. It's a large sample size.
What's a large sample?
Large sample size for me, I would say 100 is a large. So for me, I would say 100, right? Otherwise, I would use the T table. Okay. But I mean, if you had a sample size of 50 and use 1.96, I wouldn't go crazy. But at any rate, in real life, we would use a software which doesn't care, doesn't need a table, doesn't need to go reference a table, right? So I forgot where. Oh yeah, I was just demonstrating how we would do this, and that was what we say 2.064, 2.064. Okay, so let me get this out of the way. So that's 2.064, 2.064 times 7.6. And let me get my calculator out. Clear. So 2.064 times 7.6. Now that's my margin of error. Notice it's bigger, right? Before it was 14 something. I'm going to put that into memory. And I'm going to clear this. I'm going to say 151.4 minus recall memory is 135.7. 135.7. And I'm going to go back here. Clear this out. 151.4. And I'm going to add my margin of error. And that's 167.1, I'll call it. And as you can see, the confidence interval is a bit, even though it's a 95% confidence interval before, it's a little bit wider than what we got the last time. Why? Because we introduced the t value instead of the z value. We used 2.064 instead of 1.96. And we had to do this. We had no choice, because we couldn't use the z value of 1.96 because we didn't know sigma.
Could you show me how to do the standard error in this?
Yeah, so the standard error works exact. Standard error is equal to sigma over the square root of n, right? But now sigma, we don't know sigma. So the only estimate, the standard deviation of the sample, is an estimate for sigma. So we divide that by the square root of n. And we were told up at the top here, underneath my calculator there, we were told that the standard deviation of the sample happened to be 38, right? I made believe that we took, and you remember how we got the sample standard deviation? We just use Excel, for the 25, we just took the 25 numbers and found the standard deviation for the 25 numbers. Just like we would find a mean for that sample, as opposed to the entire population. So that's what really changes things.
If you gave us a series of numbers and
you'd go to Excel and calculate the mean and the standard deviation and use them to calculate your confidence, yeah, right, your standard error and then your confidence interval.
On the T-table, it says right tail probability.
Yeah, in other words, it just says, because it's just saying that one tail is this probability. And the other tail is going to be symmetrical, right? Normal distribution. So the right tail is 2.5%. The left tail is 2.5%. So what confidence level is that? It's on the column for 95%. So 5% is accounted for. So the other part is a 95%. Why they do it, I don't know, just to make it hard. You know what, just to make it confusing. Okay, so here's a graduate. Okay, this is, I think, the class of 1999 or something like that, graduated from in epidemiology. This is what I think that's a master's, right? That a PhD has a little bit more stuff on it. Based on a careful study of Night of the Living Dead, another zombie movie, it appears that zombies are predominantly male. A random sample of 100 zombies from Halloween weekend zombie movie marathons found that 58 of this sample were male. What's the point value for the proportion of male zombies? Okay, so they've probably made 7 million zombie movies. Each one of these zombies, I just saw the sequel to Zombieland, right, which is a popular movie, right? That came out a few years ago. It's a popular movie. It was very good. It happened to be very good. So I like the first one. So I went to see the second one. It's really good. Except in that movie, there's like 1 billion zombies in that movie. Like they're killing a zombie every 5 seconds in that movie. So at any rate, so there's a lot of zombies around, and you got a lot of movies. So there's a lot of millions of zombies, right? So we can't afford to go to watch every movie and count every one of them, you know, except, to be honest with you, it's every once in a while when I'm binge watching shows, I feel like I'm doing that practically anyway. So, but anyway, we can't afford to do that. So we randomly selected movies and randomly selected 100 zombies, and we recorded whether they were male or female. So it turns out that out of 100, that 58 were male, right? So what's the point value for the proportion of male zombies? It's 58 out of 100, right? Or 0.58. 58% of zombies, based on our sample, 58% of zombies are male. Okay, so I'm going to put over here, P is equal to this. The only problem with that P is the population proportion, right? So how do I distinguish what my sample proportion is from what the population proportion is? That's what I really want to know, the population of all zombies, not the 100 that I happen to randomly select. So how am I going to distinguish the P for the population from the P for my sample? Well, with X, I just put a bar. There you go. You put a hat on it, cap on it, right? So P cap represents our proportion, the point value for our proportion. Okay, so what's my confidence interval now? Now, just like a mean, we have a point value that we want to know what is the range within which I have confidence that that I've captured the true population proportion. So I'm going to say P cap plus or minus. Now, let me see, should I use T or should I use Z? What's my sample size? 100. That's a big sample size. To be honest with you, that's a relatively, when we do surveys and we do proportions like diabetic, not diabetic, our sample size tends to be very large. So in many of these kinds of problems, we will use 1.96, right, for our, hi. Nope. Okay, 1.96, right? So we use a Z table for that instead. So now I'm going to say P cap plus or minus Z for alpha is equal to 5%. Right? I'm not going to do the over 2 stuff. This over 2 is equal to 0.0, same idea as that the one side is 2.5%. So I'm just going to put alpha is equal to 0.05. Okay, so Z times our standard error. So the only thing that's tricky here is our P is 0.58, P cap is 0.58, plus or minus 1.96, because we have a large sample size, times our standard error. Now our standard error is going to be equal to, and this is a little bit different, quite a bit different, is equal to the square root of P cap, it's equal to the square root of P times 1 minus P over N. Okay, really, we don't know what P is, right? So we have to wind up using P cap here instead, because we don't know what the population proportion is. But that's okay because our sample size is large. So the standard error is equal to the square root of 0.58 times 0.42, right? 1 minus P over 100. So now I'm going to go to the videotape here, and I'm going to go to my calculator. Used to be a sportscaster, Werner, I forget his last name. Used to be on Channel 7. He used to, that was kind of his catchphrase when he was doing sports. He said, "Let's go to the videotape." And they would go to the video. I don't know if anyone, there might be somebody that's on here that's old enough to actually remember that guy. Werner, I've lost his last name. I don't remember what his last name was. Okay, so at any rate, Channel 7 eyewitnesses, I remember that at least. Okay, so I'm going to clear this out. So I'm going to say 0.58 times 0.42. You multiply it out, divide by 100 is equal to this, and then I'm going to take the square root of that. And it's equal to 0.0493. I'm going to, for my purposes, I'm going to call it 0.05. 0.049. Actually, let's stick with 0.049. Okay, it's not really 0.049. Okay, so this is going to be 1.96 times 0.049. Okay, so let me go back to my calculator. Okay. Oh, I should have left it up because then I wouldn't have to put this in again. I would have had the original number 0.04. Let me clear up memory before I 0.049. No. Lundqvist is a hockey player. Werner. It'll come to me. I'm old, but it'll come to me eventually. Might be tomorrow morning. Werner. No, Werner. Werner. And he was a sportscaster on Channel 7 News. Okay, 0.049. He was kind of a real fixture in New York. He was kind of like a popular guy. 0.049 times 1.96. Okay, so that's our margin of error is 0.09604. So I'm going to put this into memory. I'm going to clear it out. So my 95% confidence interval is 0.58 minus our margin of error, which is 0.484. Let me move this over. Point 0.484, comma, and the upper limit is going to be, clear that out, and say 0.58 plus our margin of error is 0.676.
So you multiplied and divided before you did the square root.
Well, I multiplied and divided by 100 and then took the square root of the whole thing. It's not 0.58 over 100.
No.
It's everything inside there under the square root sign.
I got a different number.
What'd you get?
My margin of error is 0.049.
Oh, no, hang on. 0.049 is your standard error.
Yeah, my standard error.
And then you multiply by 1.96.
Right.
Yeah, so you got the same thing I did, right? Okay, good. That's good. I feel better now because I was worried I wasn't right anyway. So, okay, so that's the deal there. It's just a little bit different when we're working with proportions, but we still find the same. It's still the same basic idea. So now repeat for 99 and 90% confidence intervals. What do you do there? Instead of 1.96, 2.58. Instead of 1.96, 1.64, depending on whether you want the 99% confidence interval or the 90% confidence interval. Okay, so let's move on to the real meaty stuff that we need to learn. Okay, good. Let me get this out of the way. No more zombies. What's that?
going to meteor.
Yeah, media than this, yes. Yeah. Okay.
That's pretty neat.
Okay, so, all right, so let me get this on Blackboard. Let me go to the weekly materials here. So now I'm going to go in here and I'm going to go to the stuff that's in here. Okay, so I'm going to open up this document. Okay, so here we go. So now I'm gonna propose something that is a little bit close to a real world example. Not exactly a real world example, but a little closer. And I'm gonna propose that we happen to know that we have two populations, population A and population B. Population A, um, 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 population A, we don't know what the mean is for population A. So we take a sample of 9 randomly selected subjects from population A, and this is the scores that we get for them. It could be anything. Doesn't matter what this is. It's just 9 numbers, right? From randomly selected people. So now our sample size is 9, right? So now the population that we're comparing it to has a known mean of 8, right? So if I told you that the population A and population B have the same standard deviation, we know it for population B. We know sigma is equal to 3, right? We know that that's actually what it is. If I were to tell you that sigma is equal to 3 and asked you to tell me, can I be 95% sure that the true population mean for A is different than the true population mean for sample B? Okay, let me see, how am I going to do this? Okay, so I am going to take these numbers and I'm going to open them in Excel. And in fact, I have them in Excel, I think. And here they are in Excel. Okay, so those are the same numbers we just had. I'm going to find, let's see, that's population A, right? Population B, right?
Sigma is known 3.
Yeah, sigma is known to be 3.
For
Okay.
both populations?
For both populations. Known to be 3. Sigma is equal to 3. Okay, so I'm going to go over here is the other population. The other population, mu, is known to be 8, and sigma, oops, I'll put it over here next to it, is 8, and sigma is 3. Okay, so I'm going to take a look at this. I'm going to say to myself, gee, what's the mean? What's x bar equal to here? Is equal to the average of these numbers. So x bar is equal to 9.8889 and so on and so forth, right? So I want to know, well, let's see, mu is equal to 8 for that population. X bar is our estimate of what the mean for group A is, right? So the mean for group A looks like it's a little under 10. So 8 versus 10, the difference between these two looks to be a little less than 2, right? So is that far enough apart for me to say with less than 5% chance of being wrong that these two means, the mean for group A and the mean for group B are different from one another? Well, how do I test that? The way that I test that is I say to myself, the number of standard errors apart. In other words, the Z or the T score. In this case, I know what sigma is, right? So I'm going to use the Z score. The number of standard errors apart that these two values are is the mean for equal to the mean for group A minus the mean for group B divide and put that together and divide that by the standard error. Okay, so now the problem is I don't know the mean for group A, so I have to use X bar, right? So my Z-score is going to be equal to, it's going to be equal to 9.8888 minus 8, right? And I'm going to put that in parentheses. And I'm going to divide that by the standard error. Do I know what the standard error is yet? I haven't calculated it yet, have I? Right? Okay, so let me hit escape here. And let me calculate that first. The standard error is going to be equal to sigma over the square root of the sample size. Square root of the sample size is 3. Sample size is 9. So sigma is equal to 1. I'm going to cheat a little bit here. I'm going to change one of these numbers. Hang on a second here. I'm going to change this to a 15, 11. I got a reason for cheating. Don't worry about it. It'll become obvious. Maybe not 11. Maybe I'll make it 12. That's good enough, I think. Okay, so the mean came out to be 10.66, right? Okay, so now I'm going to calculate my Z-score. My Z-score is equal to the difference between the two means. In other words, instead of mean A, I got X bar, right? So I'm going to take that. Let's see, X bar is 10.66 minus 8. I'm going to put those in parentheses and divide by the standard error, which is 1. Oops. And divide by the standard error, which is 1. Hit enter. And I come up with a Z-score of 2.66. They're 2.66 standard deviations apart. They're 2.66 standard deviations apart. So now to be 95% certain that they're different, what do you think the Z-score should be if I know sigma?
More than 1.96.
Bingo, exactly. Our critical value, our Z critical, the value for Z that I need to exceed to have less than 5% chance that we would find them to be this far apart if the two means were different it's the same in the two populations, is 1.96. Right? So that is my critical value I need to be bigger than. Okay, now I'm going to change the problem a little bit. That the two means are different, right? In other words, less than alpha is less than 0.0. The value of the probability that they would be the same value, the two means now, is less than 5%. Okay, so now you may have noticed that in the problem that I gave you, the second half of this problem says it's all the same numbers, but it says that sigma is unknown. We don't know what sigma is, right? So let's see how that complicates things here. Okay, so we had a nice margin there for 2.66. Okay, so let's go back now and take a look at how would we have solved this if we didn't know what sigma for the population would be. Well, in that case, gee, I have no choice. I got to use, instead of sigma, I got to use the standard deviation, right? What's the standard deviation? Standard deviation is equal to, I got to calculate, equals STDEV parentheses, and I'm going to take all of these over here, and the standard deviation is 2.34, right? So now, what is my standard error? My standard error is my standard deviation divided by the square root of the sample size, which is 3, comes out to be 0.78 this time. Okay, that's just how the numbers fell. Okay, so now how do I calculate my Z-score? I don't calculate my Z-score. If I don't know what sigma is, what do I have to use instead of Z? T. T is equal to X bar for group A minus the mean, known mean for group B, over the standard error. Okay, divided by the standard error. Okay, so what is our T-score for now? Our T-score is going to be, it's going to be equal to X bar, which is 10 point whatever, minus x bar b, which is known to be 8, put that in parentheses, divided by our standard error. Oh, I forgot to calculate my standard error again. Okay, let me hit escape here. First, I need to calculate my standard error. My standard error is equal to the standard deviation. Did I calculate it? Oh, I did calculate it already. I did calculate it right there. Oops.
Your standard error is
0.78, right, is equal. So t is equal to x bar 10.66 minus 8, parentheses, and then divide that by, oops. Let me try that again. Equals parentheses 10.66 minus 8. That's the difference between the two means, divided by my standard error, okay, is equal to 3.41. You know, it came out bigger because when I put that 12 in there, it kind of compressed things. So my t-score is 3.41. Now, what's my critical value of t gonna have to be? How am I going to find my critical value of t that I have to exceed in order to say that these two means are different? Bingo, you go to the table, exactly right. T, aggressivity t.
8.
Okay, aggressivity t table. Aggressivity t table. Yeah, 8 degrees of freedom, right? So what do you get? I get 2.306. So the critical value of t is 2.306. Have I exceeded my critical value of t? Yes, I have. So I can say that the two means are different, and also say there's less than 5% chance I would get this big a difference between our sample and the known mean if the original assumption that the two means are equal is true. So I can say I'm 95% certain they're really different. Okay? Now, the only thing we haven't done here is we haven't set up a null and alternative hypothesis, which we should really do right at the start. So I'm doing it at the tail end. So what is our null and alternative hypothesis? Good, exactly. Okay, now what's the mean of population B equal to?
Population
8, yeah. So I could actually abbreviate that and just say the mean of population A is equal to 8. What's our alternative hypothesis? Mean of population A is not equal to. You could say it either way. Is not equal to the mean of population B, or you could just say not equal to 8. Same thing, since you know what that is. So what happens now with this result? Both of these results, right? In both of these results, what do I wind up doing? I wind up saying I can reject the null hypothesis, which is that the mean of population is equal to 8, and accept the alternative hypothesis, that it's different than 8. In other words, different than the other population. Okay. What we just did now is called a single sample hypothesis test. And why is it called a single sample hypothesis test? Only one sample, right?
That you know.
That only one sample that we had to take. We knew the other populations mean. So we only needed to sample one of the two populations, right? So what do you think we're going to learn about next? Two sample t-tests, right? Exactly, because that's what you're going to do more often than not. You're not going to know the mean of the population of the population, right? You're going to have to do the same thing, exactly. Okay, so that's what we're going to move on. But before we move on to that, I just want to,
if the number is if it's close to the t, then it's closer to the null hypothesis.
Right, yes.
Okay.
Yes, if it's closer to the t critical value of t, it means it's closer to 5% chance that you would get that extreme a difference. So if it's 6% chance that you would get that big a difference, that's good, but you know, if your goal was to show with less than 5% chance that they could be the same, then it's a little sticky. You wouldn't reject the null hypothesis. In real life, everybody understands that that's an arbitrary number, that 5%, right? So, I mean, if you get a result that says that the difference between the two, the t-value represents 6% chance of them being wrong if you reject the null hypothesis, well, you're going to publish that anyway, right? You're just going to put in there that the t-score was this, or confidence interval was this, and so on and so forth. Remember our so now I just wanted to put it into perspective. I'll go into this on one of the next problems, I think, probably better. Okay, so now we're going to do t-test. Oh, yeah, before I do this, I want to demonstrate doing this in SPSS. Okay, so I am going to go into, I don't see any questions online yet, so, but if you guys online have a question or something like that, feel free to cut in here. Okay, or into the chat box anyway. So now let me see here. Okay, let me see if I can't find what I need. I need to go to the desktop. I need to open SPSS. I think it's under IBM. Yep. Okay, so now we're going to do the same thing with SPSS. And I have these numbers. Okay. I'm going to save this on my desktop. Yep, put that on my desktop. Okay, I'm going to say file, open, whoops, file, open, data. And I'm going to have, there's my single sample test. And this is it happens to be the original numbers, but really doesn't make that much difference for what we're going to do. So here are the numbers that we started with. And now I am going to test our null hypothesis, or alternative hypothesis. Excuse me? No, I guess I could. I think I changed it to 12 actually. Okay, I'll change it to 12 so we get the same, hopefully get the same answer. Okay, so now I'm going to do the same thing I did manually using SPSS. Here's our 12 numbers. I'm going to analyze. First of all, let me just show you the variable view. You can see it's only a single line because I'm only using a single column. It knows that it thinks it's nominal values because that's good that I looked. It thinks because the numbers are all integers that it's nominal values, like maybe those numbers represent ethnicities or something. So I got to tell it that that's scalar, those are numbers that it's reading, like values they want to find the mean of and so on, right? So I could, right now it just says X over here for the variable name. It took it off the top of the Excel file I was working with originally. In the label, I could tell it, oh, use what could this be? Let's see, what's that? Yeah, no, I meant like, what can I use in terms of what the numbers represent? What would numbers like that be? I'll just call them scores. How about learning scores? Okay, so that's what they're going to be. Those numbers represent some maybe student learning scores or something like that. So now I am going to go up to. I want to compare the mean of this population that this sample came from, to the mean of a known population that has a mean of 8. Analyze. I'm going to go, obviously, compare means. So I'm going to compare means. I'm going to go down to one sample t-test because that's what we're doing here. I'll click that and I'll go in here and I'll say, okay, let's move learning scores over to here. That's the variable that I want to work with. And what am I comparing it to? I'm comparing it to the value 8, the population that has the value 8. So that's what the test value is the other population. And I'll click OK. SPSS calculates the mean, 10.67, the standard deviation. We did the mean, I think. Oh, I didn't redo the mean when I made it 12. Right, so that's okay, don't worry about it. We're not going to go back and do that again. The standard deviation is 2.34, or maybe it auto-calculated. It auto-calculated probably. Okay, 2.34, standard error is 0.782 based on that sample size, degrees of freedom, and so on. So it calculated standard error and everything. And then down here, it calculated our t-score, 3.4, same thing we got before, right? And it said 8 degrees of freedom. And then it doesn't tell me what the critical value of t is. So how do I know whether to reject the null hypothesis or not? Right? It does. Where's the critical value of t here? I know what the t is. That looks like I should reject it, but instead of giving you the critical value of t, what it gives you is the exact probability that you would get this big a difference between the two means if the null hypothesis were true. So what we're trying to prove is that there's less than 5% chance that we would get this big a difference between 10.67 and 8 if the null hypothesis were true. So what's the probability? What's the real probability that we would get this big a difference? It's less than 1% chance that we get this big a difference. So since this is less than what percentage? 5%. Since it's less than 5%, there's less than 5% chance we'd be wrong if we reject the null hypothesis. In other words, we'd only get this big a difference between 10.67 and 8, given these 9 numbers. We'd only have a 1% chance that the means in the two populations would be the same. So we can reject the null hypothesis that the means are different. In reality, you should not state it that way, that there's less than 1% chance or 0.009 chance. You stated that there's less than 1% chance that you would get this extreme a difference between the two means. But it's still justification, since it's less than 5%, for rejecting the null hypothesis. Right? So what if this had been 9% instead of 0.09%? What would happen then? What if this had said 9% instead of 0.09? We would fail to reject the null hypothesis. We don't accept the null hypothesis. Because you're not proving that. That 9% doesn't prove that. As a matter of fact, it's still likely the null hypothesis is not true. It's just that you're only 91% sure it's not true, not 95% sure it's not true, right? So you never say, I accept the null hypothesis, because that's not what you're trying to prove. That's really not anything you're going to get from this anyway. You fail to reject the null hypothesis. That's it. So you got a couple of choices here. You can either fail to reject the null hypothesis, or you can reject the null hypothesis and at the same time accept the alternative hypothesis. Okay, let's move on from there now. So that's single sample t-test. So now how do we do a two sample t-test? Well, let's look at this paper that I have over here. How we're going to approach this. Okay, the next page here, two sample hypothesis test. Well, now look at this. We have two samples here. I don't know the standard deviation for either population of males, population of females. And I want to compare the two means. So let's start off doing this the right way. I'm going to write out a null and alternative hypothesis. H null. Sometimes they'll write that as H like that is equal to, let's see, H null. I'm not equal. I'll just put colon or something like that. Don't worry about that. That the mean for males is equal to the mean for females. Notice I use mu. I use the mean for the population. I'm not comparing X bar for males to X bar for females, because I already know that X bar and X bar for females is different, because I can just calculate it. It's going to be different. But I'm just going to use that. If they're different, I want to know if they're different enough for me to say this. I always talk about the population when I look at my hypotheses. And my alternative hypothesis is the mu for males is not equal to the mu for females. This is called a two-sided hypothesis. Why is it called two-sided? Because we're not prejudging whether the males have a higher average than the females or a lower average than the females. We're just trying to prove that they're different at this stage. Okay? So it's two-sided. Okay, so now how do I go about showing this? Okay, well, one way is, just for argument's sake, I calculate X bar. Let's say that X bar is 10. Let's say X bar for females is 8. Okay? So how am I gonna do this now? X bar, since I don't have any mu's, I know in order to find out the T value that I need, right? Because I don't know the population standard deviation. X bar for males minus X bar for females over the standard error is what my T value is gonna be. Okay? I got a couple of problems here, okay? Standard error, I gotta calculate standard error. It's equal to, well, I don't know sigma, so it's going to be equal to the standard deviation over the square root of the sample size. Okay, so what's the standard deviation? I got two groups here. Which one do I use for the standard deviation? Well, I might use one of them. How about if I combine two of them, combine both of them? Well, I can only really combine both of them if I have some reason to believe the standard deviation of males is the same as the standard deviation for females. So it's confusing now. What do I do now? And what about the sample size? What's the sample size? Is the sample size 9? Is the sample size 18? Is the sample size 8? Is it 17? What's the sample size? You're guessing. No, I meant you're guessing at which the right what the right answer is. But that's okay. Guessing's okay. Guessing's okay because I'm gonna give you the answer. It's not obvious. Okay. Well, we have a few things that can go on here. One possibility is that the two groups have equal variances, equal standard deviations of variances. And the other possibility is that they have unequal variances, unequal standard deviations. Okay, so I'm going to open this up in Excel. I have this data in an Excel file, I believe. I'm going to open it up in Excel so we can look at these numbers. Okay, so I'm going to clear this out so I'm not looking at all this stuff on here. I'm going to look at these numbers in Excel now. Let's see. Okay, let me get this out of the way. Let me minimize this. And where did I must have closed that. Here's Firefox. Oh, there it is. Good. I still got it. Okay, so I'm going to get to my two sample t-test. Save link as. Oh, actually, I don't even have to do that. I think it'll open Excel correctly from here. Okay, I think I can do this way. All right. So I'm going to go into Excel. Here's my males and females.
Is the variance the same as the standard deviation?
The variance is the square of the standard deviation, but you could use them interchangeably. Okay, in other words, I wouldn't worry about it too much. I'd use them interchangeably. Standard error is only for the sample. You got to take standard deviation divided by the square root of sample size. Okay, so now let's take a look at what the means are. Equals average. So the average for males is, okay, 10. And the average for females is 7.6 roughly. Okay, well, how about the standard deviation? That's the X bars. Okay, now how about standard deviations? The standard deviations for males is that, and the standard deviation for females is that. Okay, so now I have two possible situations here. One situation is that I could say that the standard deviations of these two populations are roughly the same, or I can say that they're different. I'm going to give you a rough rule for determining whether you should assume them to be the same, or whether to be different. When you use SPSS is going to give you a calculation that will help you decide this more accurately. But in the meantime, for our purposes, if the standard deviation of one group is not more or less than twice the other group, we're going to say they're the same. So if this is 1.94 and this is 2.7, I'm going to assume that the standard deviations are equal. If the standard deviations are equal, I can pool these two numbers into a single standard deviation. Okay, so now you're not always going to get the same sample size, right? And they're not always going to be exactly this difference and so on. So it gets a little complicated. So we use a formula to pool the two standard deviations. Basically gives us a weighted average of the two standard deviations. Okay. In addition to that, we then also need to know what are we going to use for our degrees of freedom. Our degrees of freedom, when we assume equal variances, degrees of freedom are going to be equal to the sample size equals the N1, the total sample size, plus N2 minus 2. N1 plus N2 minus 2. Okay, so how am I going to do this calculation? Well, I gave you a reference here, okay, and it's called t-test variations. It's a PDF file, and here it is. Now, this is what, it's got a bunch of these. Well, when we got a single sample, when we have a single sample t-test, it's easy. You only have one sample size, not a problem. When you got two samples, it gets a little complicated. These formulas represent what to do if you have a standard, two samples, standard deviations assumed to be equal. In other words, one's not twice the other. Okay. The next page, what formulas do you use if they're not assumed to be equal? If one group is not more than twice the other, right? This is the formula you're going to use. And then finally, also, if you're comparing two proportions, these are the formulas that you wind up using. Okay, pretty nasty looking formulas, right? That's why it's really nice to use SPSS. Okay, so I'm just going to look at this first one. I'm not going to solve it necessarily. Well, I guess how are we doing on time? So. Okay, I think I get this in. Okay, so I'm going to do this first one. So how do we do this first one? This first one, I say, okay, standard deviation is going to be equal. The first thing I'm going to do is this is our main formula right here. The t-score, right? Remember, we're still comparing it to t for, in our case, for 16 degrees of freedom, 16 degrees of freedom, right? We're still comparing it to the t-value for 16 degrees of freedom. We looked that up on the table, right? So what am I looking for? I'm taking the difference between the two means, x bar 1 minus x bar 2, x bar female minus x bar male, divided by the standard error. This number down here is the standard error. Well, the only problem is now I have to calculate standard error differently for a two-sample t-test with equal variances. First thing I have to do is calculate a pooled standard deviation. That's what SP is. How do I do that? I do this up here. So it's equal to the sample size 1 minus 1 times the standard deviation squared, right, plus N2 minus 1 times the standard deviation for group 2 squared over, that's our 16, 9 plus 9 minus 2. Okay, so if I want to do this in Excel, it would be equal to SP, pooled standard deviation equal to, and I'm going to do this this way. It's going to be equal to 8, n minus 1 is 8, times the standard deviation for males times itself squared. Okay, I'm going to put that there. And then over here, I'm going to do it for the second part. Equals 8, it's the same sample size, as it happens to be samples, times the standard deviation for females times itself. Okay, and on the bottom, we have 16, right? 9 and 9 is 18 minus 2. So that part's on top. So it's going to be equal to the square root of this plus this, over 16. Okay, but I got to make sure that I got all my parentheses, got to go around the whole thing. Also separate. And it comes out to be 2.37. That's our pooled standard deviation. What was our standard deviation for the first group? 1.94. Second group is 2.7. This one's almost right in the middle. That's not a coincidence, right? They're the same sample size, so it's pretty close to being in the middle, right? So that's now going to be our SP, pooled standard deviation. So now how do I use that now? Well, now I go to my t-score and I say, okay, what's x bar 1 minus x bar 2? Equals 10 minus 7.5. And on the bottom, I have my pooled standard deviation times the square root, pooled standard deviation, which is, what I do? I hope I didn't kill that. Okay. A is equal to, I just screwed this up, equals 10 minus 7.55. That's the top of part of our equation. Bottom part is equal to our pooled standard deviation times the square root of 1/9 plus 1/9. So close that. I got to put parentheses. Yeah, no, it'll do the inside first, then find the square root of that, then multiply. That should work. Is equal to that. So now what is our t value equal to? It's equal to x bar 1 minus x bar 2. Oops. T. It's equal to x bar 1 minus x bar 2, which is on top, divided by the standard error, which is the number I have here. It's equal to 2.18. Now the question becomes, can I reject my null hypothesis? In order to reject my null hypothesis, I have to know T critical. Okay. Do we know what T critical is? Okay, what's our degrees of freedom? N minus N1 plus N2, 18, 16 is our degrees of freedom. So we go to our T table. Oh, I got the Z table. No, I got the T table. So our degrees of freedom is 16. Our critical value of T is 2.12. 2.12. Did the value of T we calculated exceed our critical value? 2.18 versus 2.12. Yes, it did, right? Okay, it's 2.18 was the one we calculated, and it's bigger than our critical value. Since it exceeded our critical value, what can we do with our null hypothesis? We reject the null hypothesis and accept the alternative hypothesis. Now, let's do the same problem in SPSS. That was torture, right?
Could you show me how you did the degrees of freedom again?
Degrees of freedom?
Where did you get N1 and N2?
Remember that form that we had before? Okay, degrees of freedom is equal to N1 plus N2 minus 2. Okay, that's what we're using for degrees of freedom.
And where is N?
N is each of the two sample sizes. N1 is 9, there's 9 values, right? Remember the list of males and females, there's 9 males, 9 females. 18 minus 2 is 16 degrees of freedom. That's where the 2.12 came from. Okay, so let's do this in SPSS. Let me make sure I have the, okay, let me put 2 sample t-tests. And I'll put this on my desktop. And now I will go to SPSS. And I'll say File, Open Data. Go to my desktop, 2 sample t-tests. These are the same numbers as we just worked with. Here they are. Now notice how it has to be formatted differently. You see that we have 2 variables here. Unlike Excel, where we could put males and females, in SPSS, we had to put the scores and the gender, right, separately. right? So this is really ones and twos. If I change the value labels, you see it's really ones and twos. One represents, if I put them back, one represents female, two represents male, right? If I go to the variable view, you'll see the way I coded it. The values, right? These are the, I'll put in there, these are the student scores. Okay. And the student scores are scalar, they're numbers, but the gender is a nominal variable. And under values for the nominal variable, I put down 1 is equal to female, 2 is equal to male. That's how SPSS knows what those values 1 and 2 represent. So I'm going to go back here and I'm going to say, okay, the data's in there. Now I'm going to do my analysis, which took me about 12 to 15 minutes just now in Excel. I'm going to say analyze, compare means. Now this is independent samples t-test. In other words, 2 sample t-tests, 2 independent samples, one group and the other group. I'm going to put the test variable is going to be what we find the means of, which is the student scores. And the grouping variable is how they're grouped. They're grouped according to male and female. In other words, what groups they belong to. Now notice it comes up, it needs me to tell it what numbers are present that I need to work with, 1 and 2. The reason why it does that, it should be able to figure out there's only a 1 and a 2. So that's got to be 1 and 2, those grouping variables, right? It should be able to figure that out since that's all there is male and female or 1 and 2. But the reason why it asks you to tell it is because you could be dealing with, say, ethnicity, where you could have 9 different values, but you only want to compare ethnicity number 3 to ethnicity number 5. So you could just put 5 and 3 and 5 in here. But we're dealing with males versus females. I'll say, okay, SPSS goes and does the statistics. And here we go. The mean was 10 for males, was 7.6 for females in an instant. These are the standard deviations, the same as we came up with before. And down here is our t-test. Okay, so now here, let's take a look at our t-test. Now our t-test, you'll notice that there's can you see that line up there? There's a very skinny line there coming down from the E, right? Can you see that thin line, or is it hard to see? Might be hard to see online because of resolutions. But see that thin line over there? That thin line separates the t-test, which is to the right of it, from this other test called the Levene's test for the equality of variances. Remember before we just made a rough judgment, says that if standard deviations, one is not double the other, we're going to say equal variances. Well, this actually tests that assumption. So it's just like any null hypothesis. The assumption is that the variances are equal. So until you can reject that, you stick with the top line. On the bottom line, unequal variances are not equal, right? Equal variance is not assumed. You would only do that if you can reject the idea that they're equal, right? And you would reject the idea if they're equal if the significance, the probability is less than 5% that they're equal. So you need this value to be less than 0.05, just like when you do your t-test. You need that to be less than 0.05. So it's not 0.05, so we stay with equal variances. We stick with the top, right? So we stay with the top. Notice in this case, it really doesn't make any difference, right? So equal variances, so T is equal to 2.184. We know the critical value is 2.12, right? So 2.12, we know because the T value is bigger than our critical value, we can reject the null hypothesis. SPSS does it differently. It tells us the probability that we would get this extreme a difference between the two means if the two population means were the same is less than 5%. It's only 4.4%. So since this is less than 5%, what do we do with the null hypothesis? We reject the null hypothesis because it's less than 5% chance that we get this big a difference. We need this to be less than 5%, right? The smaller this is, the smaller the chance would be that we would get such a big difference if the null hypothesis were true. So if this is 1%, that's even more evidence that we can reject the null hypothesis. If it's 0.1%, it's even more evidence we can reject. But if this were 11%, that's less evidence. If it were 50%, that means there's only a 50-50 shot that we would get that big a difference if the null hypothesis were true. And we don't want to reject the null hypothesis if it's 50-50, right? We want to reject the null hypothesis only if we can be 95% sure that we'd be right. Because remember, that's an alpha error. Alpha error is a big error. Alpha error is you saying that this vaccine works. Or an alpha error says you're saying that this drug lowers blood pressure better than a placebo. And so that's a big error. You make that error, and now people are going to act on that. Usually, if you fail to reject the null hypothesis, even if you're wrong and if you had a bigger sample size, you might have been able to reject the null hypothesis. Even if you're wrong, it just means that you might have to take another look at it, another study, right? Probably not going to involve some active active interference or active intervention that costs money, could be hazardous, and so on and so forth.
Is the alpha the same alpha in the Z?
I'm sorry?
Is the alpha the same in
No, the alpha, the Z is, the alpha is, it's kind of like the Z value, except that we want it to be less than 5%, right? In other words, the Z critical, or in this case, we're calling it T critical. So the Z critical would be 5% if we knew the standard deviation of the populations. But instead we use T. So we want T to be less than 5%. We want it to be further out on the tail than just 5%. So that's why we want that number to be a small number, less than 5%. So now what about a two-tail? What about if they're unequal variances? Well, if they're unequal variances, let's see what our thing tells us. Which one is it here? I think it's this one. Let's see, we're looking at unequal variance. So let's take a look at another problem here. In this case, we're saying two sample tests, unequal variances. What do we do then? Well, now I'm going to go back to my little chart there that I made up, where you can take a look at the formulas you need to use, which is, where is it? Where did it go? I might have to open it again.
the whole thing was just for equal variance.
That whole thing was just for equal. So now what about if you're unequal variances? If you're going to do the calculation manually, right? If you're going to do the calculation manually, this is what you're going to do. You don't calculate a pooled standard deviation because you can't pool them because they're different, right? So your T value is equal to the difference in the means over the standard error. How do you calculate the standard error? Well, the top part is X bar 1 minus X bar 2, the difference in the two means. The bottom part is the square root of the standard deviation of group 1 squared over the sample size of group 1, plus the standard deviation of group 2 over the sample size of group 2. And then you combine those, so you add them together, you take the square root of the whole thing, that's your standard error. You divide that into your difference between your two means to get your T-score. You want your T-score to be bigger than your critical value of T. How do you get your critical value of T? You go to the table where your degrees of freedom. Now get a load of this formula for calculating the degrees of freedom. Take a look up there. How's that for a nasty formula, right? So, a lot of times people will just say, I don't want to bother with that. I'm just going to take the smaller sample size and subtract 1. And I know that that's super conservative, right? But if you really wanted to calculate degrees of freedom, that's what you would do. So the degrees of freedom, unlike the other one, doesn't come up a whole number. It's a calculation, right? Now, let's say SPSS. Now, I'm not going to go through this whole calculation. I'm going to let SPSS do it for me. Okay, so I'm going to go back to, where is it? I'm going to go back to here. No. There it is. Okay. And I got another one here, unequal variances. SAV file. This is the file that SAV files are SPS data files, of course. Okay, so I'm going to go back to SPSS and I'm going to open up this file. Open data. And I am going to go, there it is, two sample unequal variances. I'm going to say open. Okay, there's my two groups. And I'm going to say analyze compare means, independent samples t-test. Okay, I'm going to move variables into the test variable. I'm going to move gender into the grouping variables. Tell it it's 1s and 2s. Oops, 1 and 2. And then I'm going to say okay. And let's see what we get. We get the mean is 10. For males, 7.56 for females. The standard deviation for females is 2.7. The standard deviation for males is 1.014. Is one of those double the other one?
Yes.
Yes, it is. So this time we're going to assume unequal variances, right? So if I go down to the t-table that SPSS calculates, here it is. And notice equal variances assume. What's the significance now? What's the p-value? Probability, p-value, significance, same way, different way saying same thing, is less than 0.05. So that means I can reject that they're equal variances and use the bottom row instead of the top row, right? Equal variance is not assumed. So I go across and the t-value is 2.511. Now I could go to the degrees of, notice the degrees of freedom. It's not a whole number. Why is it not a whole number? Because SBS had to do that funny calculation to find the degrees of freedom. It comes out to be 10.152. Right? So it goes to its own internal t-table and it figures out what the probability is. And the probability is the significance, or in other words, the probability is 0.031. 0.031 is less than 5%. So what can we do with the null hypothesis? Reject it and accept the alternative hypothesis. Okay? Okay. I think, I just to let you know, there's a way to do this also with proportions. Okay, yeah, I'm not going to make you do it. I'm probably not even going to make you do it on the test. Okay, so certainly not manually, that's for sure. Where did I put it now? Keep losing track of stuff here. I have so many windows open at this stage. I think, no, I don't know. That's not it. That's not it. This could be it. No, that's not it either. Let me go to Word. Maybe it'll come up. Yep, there it is. And here is two proportions. Okay, now again, we have the situation. Oh no, that's not what I want. I want the other table. Okay, I want this t-test variations table. Okay, and if I go here, here's proportions. Okay, proportions, we want sample size of at least 30 and at least 15 in each outcome. Right? So that means, if you sample 100 people and only 10 of them are positive, that's not good enough because you want at least 15 people in the positive and negative, even if you sample 100 people, right? So there's a few rules in terms of making sure you get the right sample size. And assuming you got the right sample size, well then again, with proportions, we're dealing with only our rules are making you go for big sample sizes. Our rules. So since you're going for big sample sizes, if you're going to do this manually, you can use the Z table instead. So what's our critical value of Z going to be for 95%? 1.96. So we need to exceed 1.96. And how do we do this? We take proportion number 1 minus proportion number 2, p cap 1 minus p cap 2, over the standard error. And what's the standard error? The standard error is the square root of p cap times 1 minus p cap times 1 over n1 plus 1 over n2. And take the square root of that whole thing. Figure this whole thing out, find out what Z is equal to, and check to see if you've exceeded 1.96, if you've been successful at getting a bigger Z score than 1.96. And that's how you would do the t-test for proportions, or compare proportions using hypothesis testing. And what would the null hypothesis be? Null hypothesis would be that P1 is equal to P2, not P cap. We always use the parameter. And the alternative hypothesis is P1 is not equal to P2.
You always use population.
Yeah, in the null hypothesis, you always use mu or P. You never use X bar. Okay, because that's what you're trying to prove. You already know if the Sample means are different. All you gotta do is look at them. You can see if they're different. So you can't put x equals x1 is equal, x bar 1 is equal to x bar 2. You already know the answer to that. The real key is whether they're different enough for you to say that mu1 is different from mu2. That's what this is really all about, is proving with a certain level of reliability or certainty that you can say that the mean for group A is different from the mean for group B, right? Because then you have enormous power. Then you know if an intervention that you did, an education program, a drug, a funding of something, if that really made a difference, or if it's only that your samples just happen to be a little bit different. If you just sampled the two population, that just happened to be a little bit different.
This is starting to like sound more like epi.
Yeah, it is epi. That's exactly why you're learning this. That's exactly, in matter of fact, one of the first semesters I taught this, I taught with Susan Klitzman, she's one of the administrators now. And she taught this for a year as a combined biostatistics and epi course. And she called it EpiStat 1 and EpiStat 2. So as you were learning epi, you were learning biostatistics in parallel with it. The idea was we were hoping that you'd have more, there'd be more comprehension and more retention, especially retention. Because the problem with this stuff is that if you're taking it now, but then you take an epi course next semester or 2 semesters from now, it's hard to remember all this stuff.
Well, in epi, we did the t-test, but we didn't know what it was.
There you go. That's why this should really be a prerequisite for epi or a co-requisite, so you do them at the same time, one or the other, or at least timed so that they make sense. But now you know what the t-test is. And you know what confidence intervals are, right? So now when you read a paper or an abstract and say t is equal to this, and the p-value, sometimes they'll say p is equal to, instead of significance, they'll say p is equal to 0.031 instead of significance equals 0.03. You know that means that O is significant enough to reject the null hypothesis at alpha is equal to 5%, right? And if you know that when you see a mean is 3.7 and the confidence interval is 2 to 5, you know that that's what they got when they calculated the average for their sample. But really, you got to figure to yourself, well, we're 95% sure the real mean for the whole population between these other two numbers, not necessarily not one number they gave you as the mean. Right? Let's call it a night. Happy Halloween. It's a little late for you to go banging on doors and getting candy.